This is Chapter 14, Differential Calculus 2. This section of work in this video is covering exercise 14.1 and also does revision of some of last year's work. You need to copy out this front page into your notes and use it as a checklist for your work. Okay then. The point of this work is to understand notation for second derivatives and also to be able to differentiate a function twice. So let's get started. So here we've got y is equal to x cubed plus 2x squared plus 4. We differentiate both sides with respect to x. When we differentiate y, we get dy dx. When we differentiate a power, we multiply by the power and we put the power down 1. We multiply by the power, 2 2's are 4, and we put the power down 1. And when we differentiate a constant is equal to 0. We're now going to differentiate for the second time. So what we're going to do now is we're going to differentiate the left-hand side with respect to x. And whatever we do to the left-hand side, we always do notationally to the right-hand side. So we're differentiating both sides. When we differentiate dy dx, we end up with something which we call d2y by dx squared. Please learn that way of saying it. d2y by dx squared. When we differentiate 3x squared, we multiply by the power to get 6. We put the power down 1. When we differentiate 4x, we're just left with the 4. That's a revision of last year's work, and that is completing the second derivative. Example number 2, continuing with revision of last year's work. Now, we've got x plus 1 over x. Now, we know that 1 over x, in order to differentiate it, has to be written with the x on top. The power on the x is 1, so when we bring it to the top, it becomes minus 1. So x plus 1 over x has to be rewritten as y equals x plus x to the minus 1. Now we're going to differentiate for the first time. dy dx is equal to, well, when we differentiate x, we've got to remember there's a 1 at the front. So we differentiate 1x, we're left with 1. Here, we're going to be multiplying by the power. So multiplying by the power and then putting the power down 1. So minus 1 goes down to minus 2. So we end up with dy dx is equal to 1. The plus and the minus is a minus 1 on x to the minus 2. Now once again, revision of previous work. When we've got x to the power of minus 2, we can change that negative power into a positive power by putting it on the bottom. The 1 hasn't got any powers on it, so that remains on top. So we end up with dy dx is equal to 1 minus 1 over x squared. Okay, so that all we did there was differentiate once with a lot of rewriting. My mistake is that I should have immediately differentiated the second time rather than rewriting it. Okay, and differentiating a second time, that becomes d2y by dx squared. Differentiating a 1 becomes 0. Multiplying by the power, minus 2 on minus 1 is going to be plus 2. And then putting the power down 1, it goes down to minus 3. We'll do a rewrite now. We've got 2x to the minus 3. And because that's a negative power, we can bring it to the bottom and write it as a positive power. Because there's no power on the 2, we can just leave it as a 2 on top. So we end up with d2y by dx squared is equal to 2 over x cubed. Okay, moving on. Example number 3. So what we have here in example number 3 is we've got f of x is equal to e to the 3x plus 5. A quick bit of revision. When we have y is equal to a function of x, there is, when we differentiate an e function, the e function does not change. So we end up with just writing the e function again. And then we multiply by the differential of the power. So we then multiply this function by the differential of the power. This is the quick and easy way of doing it, and it is worth remembering. So I'm dictating to you now. You write down the e function again, and then you multiply by the differential of the power. Okay, so let's do this now. When we differentiate an f function, we get f dashed. That's how we write it notationally. So I'm now differentiating the e function. So I write down the e function, it remains unchanged, and then I multiply by the differential of the power. The differential of the power is 3, so I'm going to choose to write it at the front. I'm now differentiating for a second time, and so I write down the e function, no change, and then I multiply by the differential of the power. Differential of the power is 3, and then I just do a tidy up. If you use this method, especially if you're chasing down a H3 or higher, it makes this mathematics very, very simple, and it's well worth learning. Okay, example number 4. We're going to be differentiating twice, finding the second derivative of 2 sine x. So we're going to be finding the second derivative of 2 sine x. So over here, I'm writing down sine, cos, minus sine, minus cos. And if we're going this way, we are differentiating. So when I differentiate a sine, it becomes a cos. So g dashed x, this is a basic sine function, so it becomes 2 cos x. I'm now going to differentiate it a second time. And please note, didn't say it earlier on, but when you're differentiating twice, you will use double dash notation. So when you're differentiating twice, you use double dashed notation. And of course, the differential of cos is minus sine. So this is now equal to minus 2 sine x. Example 5. we've got y is equal to x plus 3 on 2x minus 4. Okay, that's absolutely fine. So what we're going to be doing now is we are going to could use the product rule, but quite frankly pointless, because it's quicker to expand this out and slot it in. So we've got x plus 3 over here going to our working out section, and we're going to quickly expand this. X on 2x is equal to 2x squared. X on minus 4 is minus 4x. 3 on 2x is plus 6x. And 3 on minus 4 is minus 12. Tidy it up, so we end up with 2x squared plus 2x minus 12. And then we come back down here and sub in that neat version. 2x squared plus 2x minus 12. We're going to differentiate it for the first time, so it's going to be dy dx, and multiply by the power, so it becomes 2 2's are 4. And when we differentiate a plus 2x, the x disappears and just leaves us with 2. Now, when we differentiate this for the second time, we end up with d2y by dx squared, and the differential of 4x is quite simply 4. Okay, moving on. Example number 5. This looks like the quotient rule. The quotient rule was when you're differentiating a fraction, but it isn't, because for it to be the quotient rule, now you can use the quotient rule on it, but it's much simpler if you use the chain rule. And the reason why we're going to use the chain rule is because the top is a constant. And if the top is the constant, using a chain rule is so much easier. And what we're going to do is put a power on the outside of the bracket, and we're going to bring that to the top. And it becomes x minus 6 to the power of minus 1. So y is equal to 5 on x minus 6 to the power of minus 1. Now we're going to differentiate this, and it is a function within a function. So what we have is the function inside is x minus 6, and the function on the outside is the power of minus 1. Because this function is on the outside, that's the priority, and this is the secondary function. So we're now going to differentiate this, dy dx, multiply by the power, so it's going to become minus 5 on x minus 6 to the power of minus 2. And then we're going to multiply by the differential of what's inside. Now, we've got a 1x, so the differential of what's inside is 1. Now we're just going to do a tidy up. Dy dx is equal to minus 5 on 1x minus 6 to the power of minus 2. And we're going to differentiate it again, d2y by dx squared. And again, the priority function, the outside function, is the power, and the inside function is the x minus 6. So we're going to multiply by the power. A minus 2 and a minus 5 is a plus 10. And then we put the power down 1 to minus 3. Nothing else changes. And then we multiply by the differential of what's inside. The differential of 1x is 1. Differential of minus 6 is 0. So we've now got d2y by dx squared is now equal to 10 on 1x minus 6 to the power of minus 3. we can rewrite that line because x minus 6 to the power of minus 3 can be moved to the bottom, and then that becomes x minus 6 to the power of 3, and that is d2y by dx squared. So in actual fact, there's an awful lot of rewriting in these problems. On to the next example. We're going to be differentiating a log function. So we've got y is equal to log of x squared minus 7x plus 5. So what we have here is we need to do a bit of revision on the quick way in order to differentiate a log function. Technically, for log functions, that should be a modulus sign. My apologies, not a bracket. So here we have, what's the formula for differentiating a log of a function is dy dx is equal to, you write what's inside the log on the bottom, and then you differentiate this bottom and you write the differential of the bottom on the top. I'm not going to write it out in words, I'm going to dictate it to you. Whatever's inside the log function you write on the bottom, and then you write the differential of that bottom on the top. So here we're going to do it. dy dx is the bottom is going to be, take what's inside the log and write it on the bottom, and then differentiate. So what's differential of x squared? 2x. What's differential of minus 7x? Minus 7. And now we're going to differentiate this a second time, d2y by dx squared. Now, we're going to use the quotient rule because it's a fraction. Quotient means fraction. And we've got algebraic expressions top and bottom. So we're going to quote the quotient rule using words, and it is the bottom times the differential of the top minus the top times the differential of the bottom all over the bottom squared. This is the quick way of doing it. If you learn that expression, life is so much easier. It is in the formula book. What is the bottom? Well, the bottom is x squared minus 7x plus 5. I'm now going to differentiate the bottom. The differential of the bottom is going to be 2x minus 7. Now I'm going to write the top. The top is 2x minus 7, and I'm going to differentiate the top, and the answer is 2. Now I'm going to apply it to the problem. So we have d2y by dx squared is now going to equal to, well, the bottom is going to be x squared minus 7x plus 5, and we're going to multiply that by the differential of the top. So we're going to multiply it by the differential of the top. And to make life easier and to speed things up, I'm going to multiply by the differential of the top, but I'm going to write it at the front. And then next part of the formula says a minus, so put a minus in. And it says the top, which is 2x minus 7, and then it's going to be multiplied by the differential of the bottom, so multiplied by the differential of the bottom, which is also 2x minus 7. And that is all over the bottom to be squared, which is x squared minus 7x plus 5. Now, you will 9 times out of 10, you will be expected to tidy this up in the exam. So 2 on x squared is 2x squared minus 14x plus 10. You must remember that when you write a minus sign, the golden rule is follow it with a bracket. Now 2x on 2x is 4x squared. 2x on minus 7 is minus 14x. Minus 7 on 2x, minus 14x. Minus 7 on minus 7 plus 49. All over the bottom to be squared. So the bottom is x squared minus 7x plus 5, and put the square in. Tidy up line, d2y by dx squared is equal to 2x squared minus 14x plus 10 minus 4x squared plus 14x plus 14x minus 49 all over x squared minus 7x plus 5 to be squared. So the final line, d2y by dx squared is equal to, well, 2x squared minus 4x squared is minus 2x squared. Minus 14x plus 14x cancels, so we're left with plus 14x. Plus 10 minus 49 is minus 39. All over x squared minus 7x plus 5 in brackets to be squared. Never square out the bottom when you're doing the quotient rule. Moving on. Example 8, cos function. So once again, we've got sine, cos, minus cos. When we're going down, we are differentiating. So, but we've also got a function of a function rule. So we've got y is equal to cos 5x plus 7. It's cos of 5x plus 7. So the priority function is the cos, and the secondary function is the 5x plus 7. When you are differentiating a function of a function rule, you differentiate the outside function and the inside function remains unchanged. And then you multiply by the differential of the inside function. So here we've got y is equal to cos of 5x plus 7. And we're differentiating it for the first time, so it's dy dx. Differential of cos is minus sine, so it's minus sine. So we differentiated the a part, and the b part remains unchanged, so it becomes 5x, remains 5x plus 7. And then we multiply by the differential of what's inside, which is going to be 5. So tidying this up, dy dx is equal to minus 5 on sine of 5x plus 7. And we're now going to be differentiating a minus sine function, so it becomes minus cos. So differentiating dy dx becomes d2y by dx squared. And differentiating a minus sine becomes a minus cos, but the rest of it does not change. And then we multiply by the differential of what's inside the bracket, and the differential of what's inside the bracket is 5. We then bring that 5 to the front, So it becomes 5 5s are 25 on cos of 5x plus 7. And that's the end of differentiating that. Now we're coming to the hardest example, which is example number 9. Now, this is called a differential equation because it contains differentiation within it. And we are going to have to calculate what dy dx is, then d2y by dx squared is, sub it all in, and show that it's equal to 0. So the first thing we're going to do is we're going to write down what y is equal to. Well, y is equal to x on e to the minus 2x. And this is a product rule. So the formula for the product rule from the last unit of work is first times the differential of the second function plus the second function times the differential of the first. Now the first function is equal to x, and the differential of this first function is going to be equal to, because it's 1x, it's going to be equal to 1. The second function is equal to e to the minus 2x, and the differential of the second function is, and if you remember, when you differentiate an e function, the e function remains unchanged, and then you multiply by the differential of the power. The differential of the power is minus 2. Okay then, so let's apply it. So dy dx is equal to the first, which of course is x, times the differential of the second, which is minus 2 on e to the minus 2x, plus the second function, which is e to the minus 2x, times the differential of the first function, which is equal to 1. So dy dx, tidying this line up, is minus 2x on e to the minus 2x plus 1 on e to the minus 2x. For these type of problems, you need to learn tricks, and the tricks are to factorize. So we are going to factorize this expression, which means we're going to take out e to the minus 2x as a common factor. It makes life so much easier. So dy dx is equal to taking out e to the minus 2x as a factor, leaves us with minus 2x plus 1. Now, we're going to be differentiating this expression, and once again, you can see that it is a product rule. So, what I am going to do, because I prefer to have the e to the minus 2x second, is I'm going to, and again, this is a trick, I'm going to swap these around, so it's minus 2x plus 1 on e to the minus 2x. When I differentiate this, I'm going to, for the second time, so I'm going to have d2y by dx squared. I'm going to have the first times the differential of the second plus the second times the differential of the first. The first function this time is equal to minus 2x plus 1, and the differential of this first function is going to be equal to minus 2. The second function is equal to e to the minus 2x, which of course we've already done up above. So the differential of this second function, we've already worked it out, is minus 2 on e to the minus 2x. So all we've got to do now is substitute it in. So d2y by dx squared is equal to the first, which is minus 2x plus 1 on the differential of the second, which is minus 2 on e to the minus 2x, close bracket, plus the second function, which is e to the minus 2x, times the differential of the first function, which is minus 2. I'm just going to do a little bit of tidying up on this line. So d2y by dx squared is equal to, so I'm going to bring this to the front. So it's minus 2e to the minus 2x on minus 2x plus 1. Bring the minus 2 to the front, so it's minus 2 on e to the minus 2x. And once again, the trick for this problem is to factorize. So what I'm going to do is I'm going to take out 2e to the minus 2x as a common factor. I'm going to take out 2e to the minus 2x as a common factor. So d2y by dx squared is equal to taking out 2e to the minus 2x as a common factor. Now I need to be very careful. I'm opening up a bracket. And when I take out the 2e to the minus 2x, I'm left with a minus, open bracket, minus 2x plus 1, minus. Now when I'm taking out everything, I'm left with 1. And now I'm going to do a tidy up of what's inside. So this is equal to 2e to the minus 2x, open bracket, a minus on a minus is a plus, so it's plus 2x, minus 1, then another minus 1, and then finally, last tidy up, 2e to the minus 2x on 2x minus 2. And I think I can factorize out the 2. So I'm just going to do this here. So we're going to rewrite this. So we've got d2y by dx squared is equal to 2e to the minus 2x on 2x minus 2. And what I'm going to do is I'm going to factorize out the 2 and bring it to the front. So when I bring the 2 to the front, 2 on 2 becomes 4. So this becomes 4 on e to the minus 2x. And when I take the 2 out from the x, I'm left with x. And when I take the 2 out from the 2, I'm just left with 1. Okay. So let's go to the next page and summarize these results. So at the moment, summary, I've got y is equal to x on e to the minus 2x. I have dy dx is equal to, go back and check, dy dx is equal to minus 2x plus minus 2x plus 1, minus 2x plus 1 on e to the minus 2x, and d2y by dx squared, going back to the previous page, is equal to 4e to the minus 2x on, can't remember, x minus 1. Okay, and what I've got to show is true. I need to show that d2y by dx squared plus 4 dy dx plus 4y is equal to 0. So the way we show this is we go with the left-hand side and sub in the answers. So d2y by dx squared is 4e to the minus 2x on x minus 1 plus 4 on dy dx, which is 4 on minus 2x plus 1 on e to the minus 2x plus 4 on y, so it's 4 on x e to the minus 2x. And again, the trick for solving these problems is to factorize. We have a common factor of 4. We have a common factor of the exponential. And we're going to take this out now. So we're taking out 4 as a common factor and e to the minus 2x as a common factor. And that leaves us with x minus 1 in bracket plus minus 2x plus 1 in bracket plus, we've taken out the 4, taken out e to the minus 2x, so we're just left with an x. Now we're doing a tidy up line, 4e to the minus 2x, and tidying this up, so we've got x minus 1 minus 2x plus 1 plus x. And to show that, so we have to go to the bitter end. So x minus 2x is minus x plus x is 0x. Minus 1 plus 1 is 0. So we've now got 4e to the minus 2x multiplied by 0. Anything multiplied by 0 is 0, which of course is equal to the right-hand side. Therefore, we have shown. And that's an example 9. Excellent example 9. Now that is H1, H2. If you get any of that right, you're actually working towards a H4, H5. So please persevere. It's quite doable. Now, what I need to go through with you now is first and second derivative notation. And what we have here is consider the function y is equal to f of x. And when we differentiate y equals f of x, we get a new function, dy, equal to f dash x. We did that in the last unit of work. This function measures the rate in change of y with respect to x. And the rate in change in y with respect to x gives us the slope function. So we know from last year that this is the change in y over x is the slope function. Now we're looking at what the second derivative actually means. So in terms of the second derivative, when we differentiate dy dx, we've already discovered we get a new function. So let's see how that works. What is this new function? Well, to differentiate both sides, you saw in the first example, I put a brackets around first side, and then I put dx, differentiate both sides with respect to x. When I differentiate the dy, it's pronounced d2y. And when I differentiate dy dx, it's d2y by dx squared. And this is the way we write it, d2y by dx squared. If it's function notation, then the dash goes to a double dash. Now, what is it a measure of? Well, this is the rate of change of the slope with respect to x. So what we're looking at here is the way the slope is changing. So this is very important. You need to learn this. The second derivative, this function measures the rate in change of the slope with respect to x. That's very, very, very important. Okay, so I now need you to do exercise 14.1. Yeah, so just basically whip through these questions here. So what I want everyone to do what I want everyone to do is to do this exercise here. Now, just to draw your attention to it, all that is very doable. 7 and 9 is the very last example. It is the differential equations, and that's the H1 material. Okay, thank you.